Beneath this frozen earth lays the largest discovery of oil on the North American continent in more than 40 years. Over 9,000 million barrels of it, and probably more. For over 5 years, wells were drilled and capped, no oil taken, while an oil-hungry nation waited. They awaited governmental decisions that would determine the method of transporting the oil to the refineries 2,500 miles southward. Every conventional and unconventional method for getting the oil out of the remote North Slope was considered. But most experts agreed the only practical method was by pipeline. 800 miles of 48-inch pipe had been delivered and stored along the proposed route. A $100 million investment. From Prudhoe Bay, which is locked by pack ice most of the year, the route of the line extended south into the Brooks Range, 150 miles of high, barren mountains. Then south down to the Alaskan interior, a flat plain covered with tundra. In winter, frozen rock hard. In summer, with temperatures as high as 90 degrees, it becomes a marsh, a quagmire swarming with mosquitoes. South across 800 streams and rivers, the largest the Yukon, a broad, flood-prone river over a mile wide. South up into the Alaskan Range, Thompson Pass, Keystone Canyon, and across the earthquake zones of the Chugach Mountains. South into Valdez, the southern terminus and loading point for giant tankers, which would carry the oil further south to the lower 48 states. In all, just under 800 miles, all the way down the entire Alaskan subcontinent, where the ravages of winter make lasting construction difficult. For many Alaskans, dog sleds are still an important means of transportation, as well as a popular recreation in the form of races. This is a big, sparsely populated land, much of it above the Arctic Circle. Temperatures dip to 60 degrees below zero and more. And for those who live and work in this country, survival is the first consideration. But others have argued that the first consideration for any pipeline construction work here is protection of the environment. There's a surprising variety of wildlife. Principal caribou migration patterns lie to the east and to the west of the route, but there are others: wolves, muskox, bear, sheep at the highest elevations, salmon, Arctic char, and grayling in some of the lakes and streams. And there are more species of birds than in all the rest of North America. The land itself is a study of contrast, both rugged and delicate. It's a varied and finely balanced ecosystem, sensitive to any disturbance. The tracks of a vehicle driven across this tundra might be visible for 100 years. And if the pipeline was to be built, it would have to be built in harmony with nature, designed to minimize disturbance to this environment, both during and after construction. It was a monumental task, but contractors were prepared to meet these conditions. Originally budgeted at $900 million, delays in construction and environmental protection measures increased the cost to over $9 billion. It was the costliest commercial venture in history. The Trans-Alaska project was massive in scope and diverse in its construction requirements. Yet it successfully met the challenge of 800 miles of construction, much of it in the winter. All of it built to withstand gale-force Arctic winds and deep freeze temperatures. It might well be called 800 miles of winter. It's taken its place as one of the greatest projects in construction history. Our aim is to examine some of the unique construction challenges of the project and to show how builders responded to them, to find out what it takes to build an 800-mile pipeline in less than 3 years, working virtually around the clock through bitter winter temperatures. By the first month of 1974, the stage was almost set to start the project. Construction permits were expected shortly, and at long last, the contractors and suppliers began to move in earnest. Years of anticipation and planning turned into reality as materials were marshaled for shipment to Alaska. Because of the urgency, machines were serviced in the railroad yard and on the docks. The first task, to prepare them for the extremes of Arctic duty: cold weather fluids and lubricants, enclosed batteries, induction heaters, and enclosed cabs. A full range of heavy-duty construction equipment: wheel loaders, excavators, trucks, skidders, track-type tractors, motor graders, and scrapers. Meanwhile, far to the south, more unique machines were being custom-built or tested to meet the special demands of the Arctic project. In Missouri, this mobile self-powered work platform, it tilts to match bends in the elevated sections of the pipeline. In Nebraska, a pipe layer with a telescoping crane, 2 welders' platforms, 2 400-amp welders, and an air supply for tools. It's a factory on track. In Texas, a giant chainsaw with a 14-foot blade called a rock saw was tested by cutting a trench through solid limestone, a material which closely matches permafrost. The transporter, 19 feet wide and 22 feet long, designed to carry loads up to 30 tons. In 4 months, 40,000 tons of heavy equipment, housing modules, and general cargo were barged to Alaska, then moved to Fairbanks by rail and truck. This was a race against the calendar. For unless these goods could be moved north while the ground was still frozen before the spring thaw and breakup, contractors wouldn't be ready for summer construction. Many of the first rubber-tired machines were driven north. The Yukon River, the end of a permanent road and jumping off point to the North Country. The way across the Yukon was the ice bridge. Although the surface was frozen, normal ice thickness was not strong enough to support heavy traffic. To build and maintain a safe thickness, water was added to the surface constantly. From the Yukon north, the only road was ice and snow, compacted and bladed into a passable but treacherous highway. Trucks had to be towed up the steepest grades. Prospect Creek Camp, and site of the lowest temperature ever recorded in the United States, 80 degrees below zero in 1971. These are new machines purchased and delivered nearly 5 years ago in anticipation of construction. Now they would be slowly, almost painfully, brought back to life. Engines and hydraulic systems required hours, sometimes days, of slow and cautious warm-up. To keep lubricants flowing, machines once started would be left running for days or weeks at a time. The camps were expanded: shops, living quarters, mess halls, everything to support the 3,500 workers who would build the permanent road in the spring. Dikes were built to hold 40,000-gallon bladder tanks for gasoline and diesel fuel. Over 8.5 million gallons of fuel was convoyed north. Meanwhile, aircraft of all types shuttled supplies, men, materials around the clock. Giant Hercules cargo planes made over 2,000 flights during the mobilization phase, mostly beyond the Brooks Range, where the ice road ended. In 4 months, $50 million worth of heavy construction equipment and materials was moved north of the Yukon. The work camps were established. Now the project construction could begin. Not the laying of pipe, but a road. 361 miles of new road from the Yukon River to Prudhoe Bay. The first all-weather highway to the Arctic Ocean anywhere in the world. Another 120 miles of access roads would be built, plus 11 airfields. This time, it was the road builders who'd race the clock. They'd try to complete the road before the onset of severe winter weather. Spring thaw brought the road builders long days and good weather. And although this would be one of the driest years on record, the builders faced their biggest problem, permafrost. Permafrost is ice-rich earth or rock covered by a thin layer of insulating tundra. The permafrost never melts, but the tundra in summer turns into a soft, wet marsh. The road building technique required all along the route called for an insulating gravel overlay varying in thickness from 3 to 6 feet. The road surface was spread to a width of 28 feet. Gravel was plentiful in nearby streams and riverbeds, but often this material couldn't be used. Disturbance in these areas could cause erosion and siltation, or destroy fish spawning beds. So gravel was taken from less sensitive sites where terrain disturbance was minimized. And as the road extended north and south, so did the haul distances from the acceptable sources of gravel. In many places, haul distances doubled from original plans, considerably increasing costs. 32 million cubic yards of gravel was taken from 135 storage and borrow areas to complete the road. Permanent and temporary airstrips were high priority, since until the road was completed, everything from fuel to tissue paper had to be supplied by air. Helicopters were indispensable. They traversed any terrain, from the low, soggy tundra to the high passes. Small helicopters delivered personnel or perhaps a critical spare part for a machine. Larger ones ferried construction materials. In Keystone Canyon, just north of Valdez, a sky crane delivered a D4 weighing 19,800 pounds. The larger tractors were delivered in pieces and assembled on the mountain. At the Yukon River, supplies continued to move across by hydrofoil ferry, while a permanent 2,300-foot bridge was under construction. The all-steel bridge, 20 stories high, is designed to resist moving ice packs, high winds, and earthquake stresses 5 to 15 times higher than accepted engineering levels for this location. The bridge would also carry the pipeline across the Yukon. Mile for mile, the Trans-Alaska Project was the highest concentration of construction equipment of any comparable job in history. To meet the deadline, 2 11-hour shifts, 6 and 7 days a week, were common. There was little margin for downtime. This put an extra burden on both contractors and suppliers to keep the machines running. To do it, millions of dollars in spare parts were stocked along the route, along with the skilled mechanics to make repairs at any time and in any place. A rigorous program of preventive maintenance was used on all machines. Regular inspection to detect wear to tracks and undercarriages. Engines and transmissions were checked by taking oil samples. These samples were sent to special oil laboratories, which analyzed them for abnormal contamination. Technicians were able to determine the condition of an engine and components and alert the owner to needed repair. Over 80,000 oil samples were tested here. Result, unexpected downtime was reduced and machine availability to the contractors was increased. Training was another feature of this project. Many of the workers were Alaskans who learned the specialized skills required for road building and the pipe-laying work to follow. More than 20,000 workers were trained. Meanwhile, in the seaport town of Valdez, the southern terminus of the pipeline, excavation was well underway on the new terminal facility. 1,000 acres of nearly solid rock was blasted and dug out in preparation for the construction of facilities which would store and handle the crude oil from the North Slope. When completed, the Valdez terminal will be not only the most modern oil handling facility in the world, it'll be as environmentally safe as engineers and builders can make it. On September 29, 1974, 30 miles above the Arctic Circle, supply trucks waited for the final link to be completed in the new road. The crews were justly proud of their effort. They'd completed the road in just 154 days. And as the big rigs moved north, a new snowstorm began to sweep in from the Arctic. Winter had set in. Much has been said and written about the unique construction of this pipeline. About half the line was buried, the conventional method for any pipeline. The other half was elevated on thermal piers called vertical support members. Elevation was the answer to the problem of permafrost. Oil temperature, as it traveled through the pipe, would be approximately 130 to 140 degrees Fahrenheit, hot enough to melt the frozen permafrost and create unstable conditions for buried pipe. So, wherever unstable ground was found, pipe was elevated and insulated. It would be the first pipeline to be built using this method. By all accounts, that first construction winter was the toughest on both workers and machines. The workforce had increased from 3,500 during the road building phase to over 10,000 as the pipeline phase was begun. Many of the workers had to adjust to the deep, penetrating Arctic cold. They also had to learn the limits of machines. For while men can work at minus 50 degrees, steel and rubber become increasingly brittle at 30 below and can even break like glass. The long days changed to long nights as a gravel work pad was spread along the pipeline route. The work pad protected the tundra from the heavy machines and also prevented thawing in the summers. On the north slope, gravel is particularly scarce. So to reduce the gravel requirement, styrofoam was used. Each 2-inch board has the same insulating value as 2 feet of gravel. A natural gas line was built to fuel the first 4 pump stations. The rock saw, mounted on a modified D9 tractor, cut a trench 18 inches wide, 6 foot deep, at a rate of 5 to 8 feet per minute. 70 major rivers and streams were crossed. Some were bridged, but others were crossed by burying the pipe deep below the riverbed. The winter periods were chosen for these crossings. Frozen rivers reduced the amount of siltation caused by digging. The pre-welded pipe covered by a concrete jacket was floated into position. It was then sunk and anchored. The pipe was laid up to a depth of 27 feet below the bed of the river to prevent scouring by any future storm. On more stable ground to the south, where the pipe would be buried, frozen ground was prepared for trenching by first drilling with twin pneumatic drills. The holes then charged with explosives. The hydraulic excavators then went to work clearing the trench. Tooth life in this extremely abrasive soil was as little as 2 hours. Most of the pipe was delivered with 2 40-foot sections welded together and strung out along the route. Then it was bent to conform to the ground contour by a mobile hydraulic pipe bender. The heavy-walled 48-inch pipe was shaped by a force of 3 million pounds, making bends up to 12 degrees. Close behind the bending operation followed the welding gang. On both buried pipe and elevated pipe, welding teams moved down the line, supported by several D6s with welder packages. Each section was ground and then heated in preparation for welding. 7 successive weld passes were required to build a joint which was stronger than the pipe itself. After the final pass, every weld was X-rayed and certified by hydro-testing to 125% of operating pressure. Buried pipe, before it was lowered into the trench, was cleaned and given a protective wrap. The covering protects the pipe from chemical corrosion in the ground. On On elevated sections of the pipeline, the first step was to drill holes 20 to 45 feet deep into the permafrost. Then set the 18-inch vertical support members. A slurry of sand and water was poured, which froze and anchored the pipe. The structure was completed by connecting cross beams between the vertical supports. Over 75,000 vertical support members were erected. The last operation on the elevated sections was installation of thermal insulation around the pipe. The insulation is 4-inch fiberglass bonded to a galvanized steel jacket. This is called the manipulator, a most unique, specially designed machine. It grips the insulating panels with suction cups, positions it, and carefully wraps it around the pipe until the panel is riveted into position. There were many design features built into the elevated pipe. For example, fiberglass and polyurethane modules insulate the pipe from the support members. The pipe itself is free to move laterally to allow for expansion and contraction, or in the event of an earthquake. And these are the thermal devices. Their purpose is to transfer heat from the pipe and prevent thawing of the frozen ground. Of all the physical obstacles that were overcome along the 800-mile route, most will point to Keystone Canyon and Thompson Pass, located in the Chugach Mountains, just above Valdez. In Keystone Canyon, the pipe winds nearly 4 miles along the canyon wall, 1,500 feet above the canyon floor. Access for equipment and pipe was the biggest problem. Most of the trench was dug through rock, then padded with a finely crushed gravel to protect the pipe. The work here wasn't so different from other sections of buried pipe, except that progress was slow and very careful. The final step for buried pipe sections was to fill the trench and compact the earth. On the 45-degree slopes of Thompson Pass, dozers worked in tandem, anchored by cable. Appropriately, it was called yo-yo dozing. Revegetation of all excavations had a very basic purpose: to control erosion, thus protecting the pipeline integrity. Scientists and agronomists developed specialized grasses, formulated to hold the soil until native vegetation could grow back again. For 3 winters and summers, the pipeline was pushed in all weather by a crew that had increased to over 21,000. And at Valdez Terminal, erection of the big storage tanks and facilities began to define the years of construction effort. Thus, by the end of May 1977, the pipeline was complete. Complete in the sense that it was physically connected. Hundreds of engineers, operators, and inspectors would need more time to final test and certify the sophisticated system before oil would begin to flow through the line. Loading the giant tankers goes on around the clock now at Valdez. Over 1 million barrels of oil arrive each day to be stored in tanks which hold 510,000 barrels each. Eventually, the line will deliver 2 million barrels each day, and more of these giant tanks may be needed. Operational safety, a key design element of the entire pipeline, is apparent at the terminal. Fire suppression equipment, concrete containment dikes, and a system to recover and process vapors. Shut-off valves, which automatically activate at the first sign of trouble. Environmental protection, too. This is the ballast water treatment facility. Arriving tankers must carry water to stabilize the ship in the open sea. Normally, ballast water is pumped into the harbor before loading oil. But at Valdez, the ballast water is pumped into tanks and cleaned before it's discharged into the port. At the ship berths, positive lock loading arms guard against the spill, and tanker movement in and out of Port Valdez is scheduled and watched closely by the U.S. Coast Guard. Within 24 hours of arrival, a tanker can be loaded and ready to sail with oil that came from the oil fields of the North Slope, now bound for its ultimate destination, the refineries. Yes, there was a lot of hard work in the 49th state. Not only the building of a pipeline, but also all of the associated roads, pumping stations, tank storage, and monitoring facilities. The Trans-Alaska Project is a significant achievement by any measure. For the state of Alaska, the new road is a link to remote communities in the interior. It opens the region for development of rich mineral deposits in the Brooks Range, copper, iron ore, zinc, and 1 trillion tons of coal. The pipeline itself reduces dependence on imported oil and gives us additional time to develop alternate energy resources. But the builders of the Trans-Alaska Pipeline have proved something perhaps even more important. Because of their pioneering innovations, developed out of necessity to overcome physical and environmental challenges, recovery of energy resources may now be considered possible anywhere on Earth. The technology, the tools, and the construction skills now exist to do this. And by all odds, we will need those skills in the very near future.
Turkey's useful water reserve represents the second largest hydroelectric potential in Europe. This country was hit hard by the rise in oil prices some years ago. And for several years, Turkey had to sacrifice her entire export income to pay off her oil import debts. To remedy this situation, a national energy program has been initiated. A program which provides for construction of no less than 48 hydroelectric power stations. Most of these energy projects are combined schemes. They not only produce electrical power, but in addition provide the surrounding communities controlled irrigation for agriculture. The impact on this area will be dramatic. This is the site of Ataturk, the largest of the dams proposed. As new industries are built, population will likely explode in the 6-province area. Existing cities will expand, and new ones will be built. Although southeast Turkey has remained much the same for centuries, now, due to a single new concept, a whole pattern of life is about to change forever. Of Ataturk Dam is a joint venture of 3 Turkish companies known as ATA Insat. largest dam in the world and the largest in Turkey. At a completed height of 179 meters, the total volume of fill required is 84.5 million cubic meters. Total earth-moving volume on the project will exceed 120 million cubic meters. Over 450 pieces of Caterpillar equipment are in use on the site. In 1987, a workforce of over 6,800 people were on site working for ATA Inside. With the exception of an every second Sunday holiday, work is divided into a 14-day period on a continuous 24 hours basis. Caterpillar and the Turkish dealership Çukurova provide ATA extensive product support. A resident Caterpillar project manager and a team of dealer specialists are on site to keep the large fleet producing. The support camp can provide all routine maintenance and repairs on site. Any special repairs are carried out by Çukurova at their dealership facility. For a construction site as isolated as Ataturk, the contractors had to develop all the necessary infrastructure themselves. For river diversion during construction, a cofferdam and these 3 diversion tunnels were completed in the summer of '86. At the dam site, the cliffs rise to over 380 meters and are terraced and sprayed with reinforced concrete. Outside the powerhouse, the penstocks are laid above ground. They're part of the intake structure and will be gravity fed from atop the dam's right abutment. At Ataturk Power Station is the third and largest station to be built on the Euphrates. On completion, the total electrical power production will be 2,400 megawatts from 8 turbines. Total capacity is projected to be 8.9 million kilowatt hours per year. About 1/3 of this power will be used for pumping the water needed for irrigation. The 85-ton Cat 777 trucks are the hauling workhorses on the job. The fill material is basalt rock from a quarry about 6 kilometers from the dam site. The dense basalt must be drilled and blasted before it can be handled by the wheel loaders. A total of 9 cat-powered Tamrock drills are used to sink the blast holes. Over 4 million cubic meters of overburden had to be removed to open up the quarry. The project will use over 60 million cubic meters of basalt in the total construction, with some 45 million going into the dam itself. Extended chalk deposits have been encountered at the dam site, contrary to geological expectations. As a result, an additional 6 million cubic meters of material had to be placed in just the coffer dam alone. Plans now call for a higher proportion of basalt than originally intended in the main dam. Luckily, the transportation system is up to the task. The Southeastern Anatolia project will double the amount of irrigated land, increasing production 20-fold, and generate 4 times the amount of hydropower now produced. That is expected to pay off the cost of the program within 5 years of completion. The Ataturk Dam is currently the world's largest earth-moving job. The team of Contractor, Caterpillar, and Shukurova is the best insurance for accomplishing these goals, to specifications and on time.